morning, everybody. Let's start today's session with a study at Oklahoma State University. The title of this study is Accelerated Diffusion Testing of Concrete with X-ray Imaging. Let's start with some introduction. What is diffusion? Diffusion is the movement of ions from a place with a high concentration to a place with a low concentration. Actually, this is a concentration gradient that causes ions to move towards places with a high concentration to a low concentration. So why the diffusion coefficient is important? Because diffusion coefficient is a key indicator that shows many concrete durability problems, including corrosion, sulfite attack, ASR, and freeze and thaw. The most common standard technique for measuring the diffusion coefficient is grinding test or titration, NT-build 492, which is a kind of accelerated diffusion test, and measuring ion penetration with X-ray radiography. What is the main goal of this study is accelerating the diffusion measurements of X-ray radiography. Why is this important? Imagine you can be able to measure a criteria like diffusion coefficient instead of 28 days in 6 hours. Diffusion coefficient is a trustable number that can give you a very good insight on how your concrete structure is resistant to polarized penetration. So imagine we can have a trustable number in 6 hours. Isn't it fantastic? Materials and mixtures. So in this study, we use variety of concrete structures. We use 7 Class C and 4 Class F fly ashes, both in 20 and 40% replacement. The samples are 45 days old and 3 years old. So we did the experiment in 2 different ways for making comparison. First, non-accelerated diffusion test. Then we used 104 concrete cores for non-accelerated, and we used 104 cores for accelerated diffusion test. And these cores have the same mixtures. What kind of X-ray machine this study used? So this study used chip or checking ion penetration. It's a kind of X-ray machine that is modified at Oklahoma State University to be able to do equivalent measurements as TXM or transmission X-ray microscope. How to measure the diffusion coefficient? We have concrete cores, you can see the dimensions here. We applied wax all around the sample, except the top and the bottom surface. Then we put the sample in a solution and we pour another kind of solution on top of the samples. Why we are using different solutions or different ions? Because for accelerating this process, we are going to apply a voltage differential or a battery. So we need 2 different solutions to be able to have anolyte and catalyst. Why we are using 0.6 mole per liter potassium iodide solution? So previous studies showed that the concentration profile derived from potassium iodide solution is comparable with the concentration profile coming from chloride solution. We are using potassium iodide because potassium iodide is highly X-ray attenuated. It has a large electron density. Why we are using 0.6 concentration? Because previous studies showed that this concentration doesn't have any conflict with the kind of fly ashes or fly ash replacement that we are using. So see this figure. In this figure you can see we have 0.6 mole per liter potassium iodide on top, and we have water on top. So we need a tracer with X-ray radiography to show us how that tracer is penetrating inside the concrete. Why 0.3 mole per liter sodium hydroxide solution? There is no standard test method for accelerated diffusion test with X-ray radiography. The only thing that we have is NT-build 492. NT-build 492 applied the voltage differential, it breaks the sample, it sprays silver nitrate on top of the sample, and it measures the color change. However, here we are following another procedure. We are going to have the penetration depth based on the concentration profile. But the only thing that we have right here is NT-build 492, and this is the first guess, using sodium hydroxide as our analyte. So as I mentioned before, we add a battery, we apply voltage differential, and as you can see in this image, ions with opposite charges are going to move toward ions, for example, negative to positive, positive to negative, and accelerate the procedure. Then we scan samples with chip or checking ion penetration. This is a schematic view of this X-ray machine. So this is the sample holder, detector. You can see how that X-ray looks like. Why X-ray imaging techniques are helpful? Maybe you think that using X-ray imaging would be very expensive. But in 2016, Leyes al. At Oklahoma State University, they developed a new X-ray machine that is much cheaper, more affordable. It's a kind of affordable lab equipment that can do the equivalence measurements. We don't need any powdering, grinding. It's non-destructive, it's labor-intensive, it's fast, reliable, and user-friendly. So this is a X-ray radiograph. In this figure, figure A shows a sample before funding, and figure B shows the sample after funding. Figure C shows the subtracted image. Those black spots are potassium iodide that is penetrated inside the sample. So how to measure diffusion coefficient based on the radiograph? So in this situation, we need to use gray value as a term that describes a X-ray radiograph. Gray value is a number between 0 to 254. 0 means total black and 254 means total white. In this graph, you can see the gray value is lower at the beginning and it becomes higher. Why? Because the solution penetrated. In the top part of the sample, we have solution, so the gray value is lower, and then it increases because the solution doesn't reach the depth of the sample. Then we convert gray value to attenuation. This is the equation that we use for converting the gray value to attenuation. Then we made some samples with known amount of potassium iodide inside them. We measured the attenuation and we plotted the concentration calibration curve. By using the concentration calibration curve, we can convert the gray value data to concentration profile, and having the profile like this. This is iodide concentration, which is plotted to the depth. For a non-accelerated diffusion test, we will usually fit a curve which is derived from fifth second law. It's a nonlinear regression model derived from fifth second law on our concentration data. So after fitting this fit on the data, you can see the diffusion coefficient is the slope of that curve. For accelerated diffusion test, we are using the same equations that NC Build 492 used. As I explained before, they are measuring the penetration depth based on the color change after spraying silver nitrate. However, in this study, we are going to use the concentration profile. Therefore, in this equation, we are looking for a combination of XD, CD, and C0 in a way to provide us similar results as non-accelerated diffusion. XD is the penetration depth at CD, or a concentration that is responded to the penetration depth, and C0 is the surface concentration. So we need to find a good combination of these numbers to be able to have a same number as non-accelerated diffusion. Therefore, we use a linear regression model. We define beta as a factor that divided diffusion coefficient of non-accelerated tests to the accelerated. We are looking for a beta that is close to 1 with a high possible R-square. This table shows the results of 6 hours of accelerated funding on all of those mixtures that I talked about. We changed C0 from 3.5 to 4.5, and we changed CD from 0.5 to 1.5. As you can see here, the closest number to 1 happens when we had CD equal to 1.25 and C0 equal to 3.5. The beta is 1 and the R square is 0.96. Then we use those numbers, 1.25, 3.5. We measured the penetration depth for each mixture separately, and then we calculated the diffusion coefficient of accelerated diffusion. Then we plotted this data in this graph. In x-axis, we can see accelerated, and in y-axis, we can see non-accelerated diffusion coefficient. The line here is the line x equal to y. And you can see how those data are distributed around this line with the R-square of 0.96. However, we have some red points here that they are showing a diffusion coefficient lower than 1 times 10 power minus 12. So this diffusion coefficient is very low for those red numbers, and it is happening because the samples were 3 years old and they had 40% of excess light. So we are not sure how the accelerated diffusion is going to respond for these samples. However, we need to perform more experiments to be able to judge these. We need to do more studies on these to see how it is responding. So why is this important? So measuring the diffusion coefficient in 6 hours, having a trustable data for a wide variety of samples except those that are showing a very low amount of diffusion coefficient. It's very important for industry, having numbers in 6 hours instead of 28 days of findings, and having the test method that is very easy to measure the diffusion coefficient. It is very important to have this kind of test method. In conclusion, 6 hours of accelerated finding can provide us results that are comparable with non-accelerated diffusions. If we use correct parameters for C0, CV, and XD, we can calculate the diffusion coefficient in a way that we calculated previously with non-accelerated diffusion. And as you saw here, we use variety of mixtures, different kind of fly ashes, different replacement of fly ashes, and you saw that accelerated diffusion test didn't change the results regardless of the fly ash type, fly ash replacement, or the age of the sample. These are some selected references, and thank you if you have a question.